According to the National Electrical Code, specifically Table 310.15b3, a derating of conductors is typically required when installed in conduits or raceways passing through metal studs or joists. This is because metal components can act as a heat sink, drawing heat away from the conductors and potentially causing them to overheat. However, if the conduit does not pass through any metal, this heat sink effect is absent, mitigating the risk of overheating from that source. In the specific scenario of paralleling 13.1/0 copper THWN conductors, all of the same phase, within a 4-inch PVC conduit that does not penetrate any metal, the primary concern shifts to the current load. If the current is evenly distributed among the parallel conductors, there should be no overloading, assuming the installation adheres to all other applicable NEC requirements. The heat generation within a conductor is primarily due to its resistance to the flow of current. This is governed by Joule's law, where the power dissipated as heat is equal to the square of the current multiplied by the resistance, often expressed as A squared R. Several factors influence the resistance of a conductor, including its material, length, cross-sectional area, and temperature. Copper is a widely used conductor due to its low resistivity. Increasing the length of a conductor increases its resistance, while increasing its cross-sectional area decreases its resistance. Temperature also plays a role, as the resistance of most conductors increases with temperature. When conductors are placed in close proximity as they are in a conduit, heat generated by one conductor can affect the temperature and thus the resistance of the others. This mutual heating is a key reason for derating conductors when multiple current-carrying conductors are bundled together. However, in this scenario, with the absence of a metallic heat sink and assuming balanced current distribution, the primary source of heat would be from the current flowing through the conductors. The National Electrical Code provides tables and guidelines for determining the ampacity of conductors based on their size, insulation type, and operating temperature. It's crucial to ensure that the selected conductors and their ampacity, even without derating, are adequate for the intended load. Additionally, proper termination and connection methods are essential to minimize resistance at connection points, which can also lead to localized heating. Factors to consider when determining whether derating is necessary are firstly, the ambient temperature. Higher ambient temperatures reduce the heat dissipation capacity of the conductors, making derating more critical. Secondly, the number of current-carrying conductors in the conduit. More conductors generate more heat, necessitating derating. Thirdly, the type of insulation. Different insulation types have different temperature ratings, which affects their ampacity. Fourthly, the conduit fill. Overfilled conduits restrict airflow and reduce heat dissipation. Fifthly, the presence of metal objects near the conduit, which can act as heat sinks. In the context of the provided question, since the conduit is PVC and doesn't pass through metal, the heat sink effect is negligible. The equal distribution of current across the 13 parallel conductors would also reduce the likelihood of any single conductor overheating due to excessive current flow. However, it's crucial to confirm that the installation meets all other NEC requirements, including proper conductor sizing, overcurrent protection, and grounding. Before making a final decision, one should consult the relevant NEC tables and articles to determine the appropriate ampacity adjustments for the specific installation conditions. Specifically, Table 310.15 addresses ampacity correction factors for ambient temperature, and Table 310.15b3 addresses adjustment factors for the number of current-carrying conductors in a raceway or cable. While the absence of a metallic heatsink and the equal distribution of current mitigate the need for derating in this specific scenario, the overall installation must still comply with all other applicable NEC requirements to ensure safety and prevent overheating. It is also important to know that local codes or regulations may have additional requirements that must be followed. Always consult with a qualified electrical inspector to ensure compliance with all applicable codes and standards. Now let's delve into the NEC articles pertaining to conductor ampacity and paralleling. Article 310 covers conductors for general wiring, including ampacity, derating factors, and installation requirements. Article 310.15 outlines the procedures for determining conductor ampacity based on the allowable temperature rating of the conductor installation. The ampacity values listed in the tables are based on specific conditions, such as an ambient temperature of 30 degrees Celsius and no more than 3 current carrying conductors in a raceway. If the actual conditions differ from these, the ampacity must be adjusted accordingly. To determine the ampacity of the 1/0 copper THWN conductors, you would typically refer to Table 310.16 in the NEC. This table provides ampacity values for various conductor sizes and insulation types based on their temperature ratings. For example, a 1/0 copper THWN conductor with a 75 degrees Celsius rating has an ampacity of 150 amps under the conditions specified in the table. However, as mentioned earlier, these values must be adjusted for ambient temperature and the number of current carrying conductors. Article 310.15b3 provides adjustment factors for the number of current carrying conductors in a raceway or cable. These factors are applied to the ampacity values from Table 310.16 to account for the heating effect of multiple conductors in close proximity. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity must be reduced to 80% of the value in Table 310.16. In the case of the Teen 1/0 copper THWN conductors, all carrying current, the adjustment factor would be significant. However, the key point is that the absence of a metallic heat sink and the equal distribution of current among the conductors can mitigate the need for derating in this specific scenario. Article 310.10h addresses the paralleling of conductors. This section of the NEC outlines the requirements for paralleling conductors to increase ampacity. When conductors are paralleled, they must meet certain criteria to ensure that the current is evenly distributed among them and that the overall insulation is safe and reliable. According to 310.10h, conductors must be the same length, conductor material, same size and circular mill area, same insulation type and terminated in the same manner. These requirements are intended to ensure that each conductor carries its share of the load and that there are no imbalances that could lead to overheating or other problems. In addition to the requirements in 310.10h, there are other considerations when paralleling conductors. It's important to ensure that the conductors are properly sized for the load and that the overcurrent protection is adequate. The NEC provides guidance on selecting the appropriate size of overcurrent protection devices for parallel conductor installations. Furthermore, proper termination and connection methods are essential to minimize resistance at connection points. High resistance connections can generate excessive heat and lead to equipment failure. In summary, while derating is generally required when multiple current carrying conductors are installed in a raceway, the specific scenario of paralleling 1/0 copper THWN conductors in a 4-inch PVC conduit that does not pass through metal may not require derating, provided that the current is evenly distributed among the conductors and that all other applicable NEC requirements are met. It's crucial to consult the relevant NEC tables and articles, as well as a qualified electrical inspector, to determine the appropriate ampacity adjustments and ensure compliance with all applicable codes and standards. The primary reason for derating conductors is to prevent overheating, which can damage the insulation and lead to equipment failure or even fires. When conductors are installed in close proximity, the heat generated by each conductor can raise the temperature of the others, reducing their ampacity. Derating factors are applied to the ampacity values in the NEC tables to account for this heating effect. In situations where the heat dissipation is limited, such as when conductors are installed in a conduit that is buried or passes through insulation, derating is even more critical. However, in the absence of a metallic heat sink and with the equal distribution of current among the conductors, the heat dissipation may be sufficient to prevent overheating, even without derating. It is important to consider the entire electrical system when determining whether derating is necessary. The load in the circuit, the ambient temperature, the type of equipment being served, and the overall design of the installation all play a role in determining the appropriate ampacity of the conductors. A qualified electrical engineer or inspector can assess these factors and provide guidance on whether derating is required. It is important to remember that the NEC is a minimum standard and that additional safety measures may be necessary in certain situations. Always err on the side of caution when it comes to electrical safety, and consult with a qualified professional if you have any doubts. In conclusion, while the NEC provides specific guidelines for derating conductors, the specific scenario of paralleling 13.1/0 copper THWN conductors in a 4-inch PVC conduit that does not pass through metal may not require derating, provided that the current is evenly distributed among the conductors and that all other applicable NEC requirements are met. The absence of a metallic heatsink and the equal distribution of current can mitigate the need for derating in this specific scenario. However, it's crucial to consult the relevant NEC tables and articles, as well as a qualified electrical inspector, to determine the appropriate ampacity adjustments and ensure compliance with all applicable codes and standards. By understanding the principles of conductor ampacity, derating factors, and the requirements of the NEC, you can ensure that your electrical installations are safe, reliable, and compliant with applicable codes and standards. Remember to always prioritize safety and consult with a qualified professional if you have any questions or concerns. Electrical safety is paramount, and proper planning and installation are essential to prevent accidents and ensure the safe operation of electrical systems.